Well, heidi ho, good chemistry neighbors. You guys probably don't know the reference to that old show with Tim Allen, Tim the Toolman Taylor, called Home Improvements. Check it out. All right, today, Wednesday, May 13th, 2020. We're wrapping up our chapter. So today, we're going to look at how electronegativity influences the type of bond between atoms. You know, I want you to have an understanding of how electronegativity affects things. What does it mean for a bond or a molecule to be polar? And I can name and define some intermolecular forces. All right. So I found this chart of electronegativities. Okay. Let's review. Electronegativity is a numeric scale that represents the attraction an atom has for electrons that it's sharing with another atom. Okay, so if we have two atoms forming a bond, both atoms are attracted to those electrons. The amount of attraction is on this scale, and it's a 4-point scale. So the most electronegative element on the planet is fluorine with a value of 4.0, and the least electronegative element on the planet would be over here at cesium with a value of about 0.7. Okay? There are no atoms that have an electronegativity of 0. All atoms have some attraction for electrons. And you can see that the overall trend is that as you go over and up, the electronegativity tends to get higher. So these are things we talked about back in our periodic table chapter. All right, so let's think of a bond between two chlorine atoms. So here's a chlorine atom, and here's a chlorine atom. And we know chlorine has 7 valence electrons. Chlorine has 7 valence electrons. And so we see that they're going to, we understand from covalent bonding that they both want another electron and they're going to share these electrons between them. Now, let's think about the electronegativity. Chlorine has an electronegativity value of 3.0. Okay, so this atom, the measurement of its attraction for these shared electrons is 3.0, and this atom, the measurement of its attraction is 3.0. So they have equal attraction for these electrons. So what we can kind of think about is that the electrons are kind of equally dispersed. Boy, that didn't look really equal. Equally dispersed on this molecule. Let's compare that to some other things. What if I had bromine and chlorine? Okay, bromine, red would be good for bromine, Br, and it's got 7 valence electrons. Chlorine, 7 valence electrons. We can say they would share a pair of electrons. If I go back to our electronegativity, chlorine has a 3.0 for electronegativity, bromine has a 2.8. So 3.0, 2.8. That means is that chlorine attracts these electrons a little more strongly than bromine. Okay? So if I try to draw electron distribution, let's imagine that the electrons spend a little bit more time over there than they do over here. It's not quite uniform, but it's a real small difference. Small difference. Let's try another one. How about hydrogen and chlorine? Okay. Chlorine, 7 valence electrons. Hydrogen, 1 valence electron. They're going to share that pair of electrons. Let's look at electronegativities. Chlorine's a 3.0, hydrogen's a 2.1. 0.9. It's getting to be a bigger difference. So they're going to share electrons, but it's not necessarily an equal sharing. And if I try to draw that distribution, maybe it's, the hydrogen's kind of holding on to the electrons, but really the electrons are going to spend more time over here by chlorine. Sodium and chlorine. Chlorine, 7 valence electrons. Sodium, 1 valence electron. Sort of see that attraction there. If we look at the electronegativity numbers, sodium has a 0.9. Chlorine's at 3.0. Yeah, 0.9, 3.0. The difference between the two values is up to 2.1. And at this point, effectively, what we think, the way we describe it, is that electron, it's not just even shared anymore, it's been taken away. So the electron distribution is kind of like, it's all here. So the bigger the difference in electronegativity, the more imbalanced this is. And in this case, we formed a negative ion and a positive ion. But can you see that really there's a continuum of everything in between? So in a case where there's a big difference in electronegativity, one atom takes the electrons away from the other, we have ions. If I go the other extreme, would be if they have equal electronegativity, and then we have an equal sharing, an equal distribution. So the true covalent bond is at this end where there's this equal distribution. Ionic bond is where there's a very big difference. All right. Let's try to move forward then. So if we put this as a continuum, where we look at the electronegativity difference. Remember, it's a 4-point scale, so the smallest difference is 0. If I have two atoms that have the same electronegativity, so please understand I'm highlighting the word difference. The electronegativity, it's not dependent on just one atom, it's the difference between the two atoms. If the difference is 0, that's 100% covalent. If the difference were 4.0, that's 100% ionic. But you're never going to get a difference of 4.0 because all atoms have some attraction. So our human brains, we like to draw lines to try to separate things into categories. Remember, it's a continuum, but we draw lines. So here's some places where we draw lines. If the difference between the two is about 2.0, we say that beyond that is ionic, and over here is covalent. But then, remember, this isn't going to be quite equal through here. It's only truly covalent, 100% covalent if it's a 0. So we draw in some other lines, and we call this area polar covalent, and I'm going to explain that. Polar covalent is a covalent bond, so there's a sharing, but it's an unequal sharing of electrons between the atoms. One atom has a stronger attraction for electrons than the other. Okay? It's kind of like if you and I buy a car together. We both chip in on the car, but I get to use the car every day from 6 a.m. to midnight and all weekend. And you get to use it the rest of the time. That would not be an equal sharing. The car spends much more time with me than with you. Okay? Works out great for me, not so good for you. So the electrons are spending more time with one atom than another. Polar covalent. Why polar? Well, the word polar means it has ends. And so if you have a polar covalent bond, the electrons spend more time at one side than the other. So that side is a little bit negative relative to the other side, which is a little bit positive. It's not a full ionic charge. It's not fully a negative charge and a positive charge, but it's a little bit negative and a little bit positive. It doesn't work very good when I show a video and record a video showing a video. So, it's a fun little video. Look up Dogs Teaching Chemistry on YouTube. It's a good one. All right, so here's where we draw our lines. If the difference is 0.4 and less, we're going to say that's so close to an equal sharing of electrons that we're going to call it nonpolar covalent. The only true nonpolar covalent bond is if it's 0. But these are close enough that we say, good enough. And then when we go between 0.4 and 2.0, we're going to call it polar covalent. And above 2.0, we're going to call it ionic. However, that 2.0 is a little bit fuzzy also, because if one of the elements is a metal, we instead of 2.0, we use a guideline of 1.7. So anything beyond 1.7 to 4.0 is going to be considered ionic if there's a metal involved. Yeah, I know, it's complicated. And then students ask me, well, what if it's exactly 0.4? I don't know. What I usually do is say, maybe it's just slightly polar. We just use some extra terms or extra words to go with it. Here's just another representation. So these shapes are trying to show the electron distribution or charge distribution. And if it's a pure nonpolar covalent bond, you have this kind of symmetrical distribution of charge. If you got a polar covalent, this side's more negative and this side's more positive. And if you have ionic, you've formed separate ions. All right. Remember, a molecule is a neutral group of covalently bonded atoms. Okay? But you can have polar bonds on a molecule, and water is just truly the prime example of a polar molecule. Water is so important in its bonding and its special properties. It's because water is polar that allows us to be here. If water were not polar, life on this planet would not be here, period. So look at the shape of this. Remember, these unshared pairs repel these other electrons. Now, if you look at this bond, hydrogen has an electronegativity of about 2.1. Yeah, I've got it up here. Oxygen has an electronegativity of about 3.5. So the difference is 1.4. And when you look at 1.4, that's getting pretty substantial. So this is a very polar bond. And it means that the electrons of this shared pair are being pulled towards oxygen. Well, there's another bond, but those electrons are being pulled towards oxygen. So the oxygen end is rather negative, and the hydrogen side is rather positive. And so this little squiggly D, that means partial negative. Okay? Symbol from math and science. And so that means a partially positive. It's a Greek letter, a lowercase Greek letter delta is what that is. And it's used for partial. This is kind of previewing a little bit when we look at the shape of molecules. You see, because of this imbalanced shape, that bent molecule for water, we can draw a line such that we can see that there's a negative side and a positive side. With something like carbon dioxide, it turns out that this bond is polar. Carbon is 2.5, oxygen is 3.5, difference of 1.0. That's a moderately polar bond. But look at the shape of the molecule, it's linear. And so really we see it's negative on that side and it's negative on that side. And that's going to affect how these molecules fit together. these molecules are going to rather strongly attract each other because the positive end of one is attracted to the negative end of the other. This guy, both ends are negative. So how's it going to feel about a neighboring molecule which both ends are negative? Doesn't like them. These guys split apart, which is why carbon dioxide is a gas at room temperature. Molecules don't like each other very well. Water is a liquid at room temperature because those particles like each other a lot and they cling to each other. So here's our chart again because I wanted it handy for this. So I'd like you to take a couple minutes, maybe write down what these sample elements are, and then I'll go to this, and you can look at the electronegativities, and I'm worried that you're going to maybe not be able to read these. So I'm going to talk through them. Okay, the first one says calcium and fluorine. Calcium is 1.0, fluorine is 4.0. Sulfur and oxygen. Sulfur is 2.5, oxygen is 3.5. Hydrogen and carbon. Hydrogen is 2.1, carbon is 2.5. Phosphorus and fluorine. Well, we know fluorine is 4.0. I know carbon is 2.5. Phosphorus is 2.1. And while I was on that last page, I looked at chlorine, was 3.0. And then I got iron and cobalt, 1.8 and 1.9. Okay, so I want you to take just a minute and look through and say, what type of bond would you expect? I'll wait for you. I guess I should have said pause the video and do that. Hope you did. If not, do it. But we'll be back. All right, so what do we look at? Hey, we got an electronegativity difference of 3.0. That's ionic. We got an electronegativity difference of 1.0. Polar covalent. Electronegativity difference of 0.4. That's one of those tough ones. It's right on the borderline. So I'm going to say, slightly polar. I will try to avoid, for a test question, I'll try to avoid it being right on the borderline like that. Difference of 1.9. Okay. Now we got to look at, is either of them a metal? And no, it's not. So 1.9, and they're both nonmetals, is still going to qualify as polar covalent. If one of those was a metal, it'd be a different story. Carbon and chlorine, difference of 0.5. So it's polar. I could also here say slightly polar. And then you say iron and cobalt, difference of 0.1. You say, that's non-polar covalent, right? No, it's not. Because we got to realize that that's a metal and that's a metal. That's a metallic bond. Did I trick you? I threw that in there deliberately, though, to get you thinking about, oh yeah, we do have to recognize where these things are coming from. This is a case where both of the metals, or both of the atoms, don't have much attraction for electrons. That's metallic bond, okay? So you do have to pay attention. All right. Now, let's take it one step further and talk about polar molecules. So, if we just look at electronegativity difference of the atoms, we can decide if a bond is polar. If the bond has oppositely charged ends, the bond is polar. That may or may not relate to the molecule. Well, it relates, but it doesn't necessarily mean that the molecule is polar, because we need two conditions for the molecule. One, you have to have polar bonds. Okay? Two, there has to be some sort of asymmetry. Okay? Not symmetrical. And if you have unshared pairs of electrons, that's going to lead to this. So what if we just look at a model like this? Here's methane. This is carbon and hydrogen, and if we look at our numbers, we know that there's a difference of 0.4 for the electronegativity differences. 0.4. By the way, I will get you a copy of an electronegativity table to look at when you're doing tests. So this bond, you could say, is just slightly polar. It's right on the borderline, but slightly polar, where the electrons are being pulled this way. So this would be a little bit negative compared to this end. But then there's another one, and another one, and another one. So if we said that this bond was polar, is this molecule polar? And the thing is, while this is a little bit positive here, this is also a little positive here, and this is a little positive, and this is a little... There is no ends, there's not two different ends to the molecule. There's two different ends to that bond, but as far as the molecule is concerned, no matter which way you come at this molecule from the outside, you're always going to experience a little bit of excess positive. There's no negative end. And so even though it's got polar bonds, the molecule is not polar because of its symmetry. Now what happens if you change the molecule to something like ammonia, where there's a nitrogen and there's hydrogens? This is a polar bond, so is this, but this is an unshared pair of electrons. And we say these electrons are being pulled more strongly towards the nitrogen than the hydrogen. And so if I look at it like this, it looks very symmetrical. You got positive, positive, positive. But if you look at it like this, you say, hey, this end is positive, but this end is negative. I can find a positive and a negative end. And if that's the case, if I had two of these, the negative end of this one is very attracted to the positive end of this one, and these molecules are going to cling to each other. Okay? So for a polar bond, you have to have, or for a polar molecule, you have to have polar bonds, but you also have to have some sort of asymmetry. All right, so let's imagine we got a bunch of polar molecules. So I'm not drawing the structure out for everything. I'm just saying this blob represents a molecule, and it's got a positive and a negative end. Well, the positive end is going to be attracted to the negative ends of these. And negative end is going to be attracted to positive ends. And positive end is attracted to negative ends. And negative end is attracted to positive ends. And you see that overall, can you see that negative becomes surrounded by positive, and positive becomes surrounded by, kind of like our crystal lattice? These molecules want to cling to each other, and clinging to each other makes them want to turn from gas to liquid and liquid to solid. These things are going to have a much higher melting point and boiling point because they're polar. Water is a very, very simple molecule. Anything else as simple as water is a gas at room temperature. I can't think of any exceptions to that. But here's water. It doesn't boil until you get to 100 degrees Celsius because the water molecules are very strongly attracted to each other. If you've got nonpolar molecules, there's no attractions. So nonpolar molecules become gases really easy. All right, so this leads into the idea of intermolecular forces. So first of all, we had bonds, right? Covalent bonds are bonds within a molecule that are holding the individual atoms together. Those are very strong. Intermolecular forces are the attachments or attractions between molecules. They're not as strong as bonds, but they can be substantial. So, most common type is called dipole-dipole forces. I know you want to look at that and say dipole-dipole, but it's dipole-dipole. Di means two. So a dipole is a molecule that's got two ends. Dipole. And if you've got oppositely charged ends, the oppositely charged ends attract to the oppositely charged end of the next molecule, and so the molecules cling together. Yep. Now, really, all of our intermolecular forces come down to kind of variations of this. So we're going to talk about one variation that's especially strong. It's called hydrogen bonding, and it is a dipole-dipole force, but it's really strong. And it's what happens when hydrogen, remember hydrogen is the simplest atom. It's got one proton, one electron. What happens if you start pulling that one single electron away from hydrogen? You have a bare proton, no other electrons to hide it. This is kind of like having a Snickers just sitting out on a plate with no broccoli around it whatsoever to repel me, right? You know, just a Snickers. I really want it. Okay? Now, look at these two water molecules. Okay? Here's a hydrogen. Its one and only electron is being pulled that way, leaving a positive. Look over here, we've got a negative oxygen plus these unshared electron pairs over here. This is very negative, and there's a really strong attraction. Now, it's even more critical when hydrogen is bonded to one of the most electronegative elements on the planet. Okay? Oxygen is the second most electronegative element on the planet, after fluorine. So if hydrogen is bonded to fluorine, oxygen, nitrogen and chlorine are the next two highest. That's where these attractions, they're dipole-dipole attractions, but we give them a different name. We call it hydrogen bonding. And water is our prime example. Water behaves different from just about anything else because of the strong hydrogen bonding in it. Lucky for us. Okay? And then we've got dispersion forces, sometimes referred to as van der Waals forces, or London dispersion forces, named for the people that worked on this. This is a bit tougher, but so let's just imagine we've got a nonpolar atom or a nonpolar molecule, and you know that electrons aren't locked up in place. So can you imagine at some point in time where just through random chance there might be more electrons on one side than the other? And at that instant, that side of that molecule is a little bit negative and the other side is a little bit positive. Well, that now influences the neighbor, because the electrons in the neighbor are saying, hey, there's a little extra positive over there, I think I'll go that way, which now induces a little bit of a negative on this side, and then that's going to be a positive on the other side. So just these temporary random fluctuations can create temporary dipoles, very weak. But this is what explains how even nonpolar molecules, if you cool them far enough, they will start to cling together and form a liquid also. You might ask yourself, well, why is there any attraction between them? Well, this random fluctuation creates those attractions. Dispersion forces, van der Waals forces, very weak, temporary, but still noticeable. Even hydrogen molecules, if you cool them to almost absolute zero, even helium atoms, if you cool them to almost absolute zero, do form into a liquid. And that's it. I got a feeling this was kind of a long one again. I haven't looked at the time. Thank you for bearing with me. I thought about, could I abbreviate this section, and I decided no, I can't, because the idea of polar bonding, it makes us who we are. If you've studied biology, you know that there's surrounding your cell walls, there's these phospholipids, and the phosphate part is somewhat polar, and it's attracted to water, but then the lipid part is nonpolar and sticks into the cell, and these things create our cell walls. Now, I'm not a biology person, so I hope I didn't say that too terribly wrong, but I mean, this is part of the chemistry of life here, because some molecules are polar. So I thought, no, I had to go into this yet. We are going for a test on Friday. If you have questions, you need to let me know so I can address them. Take care.